All right, so this is going over the quiz that we had in class, just going over which um, the answers to all of that. Let me quickly just adjust the focus here. All right, that looks well good. Okay, so I'm going to go over the questions from the quiz. So the multiple choice, which of the following is not a true statement about a standing wave? First of all, it's important to know that we're looking for a statement that's not true. So the first option, a standing wave is formed by the superposition of two progressive waves. We know that to be true. If we have a wave coming in and a wave, and that wave is going to reflect off of a boundary. This is what produces our standing waves with nodes and antinodes. So we know that it couldn't possibly be A. B, a standing wave stores energy but does not transfer it. This is also true. A standing wave, when you look at it, when you see it oscillating, it just oscillates up and down. It doesn't actually oscillate forward or backward. And this is because part of the wave transfers energy forward, but part of the wave transfers energy backward, so it couldn't be B. Now, even if you hadn't figured this out, C is says the wavelength of the standing wave is the distance between adjacent nodes. So if we were to look at our standing wave, a node is an area where there's no motion, where the displacement from the equilibrium is zero. So we look between two nodes, we can actually see that that's not a wavelength. A wavelength would be from here to here. So between two nodes, we only have half of a wavelength. So right away, C is not true, but just to go through and check D, it says the amplitude of vibration varies along a standing wave. And what that means is that the amplitude is different at different points, and that's actually also true. So the only one that's false is C. Okay. So number 2, the diagram below shows two wave pulses moving towards each other. And which of the following diagrams shows the resultant pulse when the two waves are superimposed? Okay, so if we were to draw these over top of each other, again remembering that anything below kind of acts like a hole we've dug, shape is going to fall into the hole. So we want a shape that is somehow destructive interference, because we have one wave that's below the equilibrium and one wave that's above, and that crosses out C and D because these are both what looks to be constructive interference. So it has to be A or B. Now, here we have a box drop down with that humped wave kind of sitting in the bottom of it, and this is actually the correct answer. It's B, and the answer is not A. Okay, this was a really tricky one, and actually kind of had a bit of a trick to it. Which wavefront diagram best describes a longitudinal wave traveling to the left? Now, what we have to remember is that this is a wavefront diagram. So, regardless of whether we're talking about longitudinal or transversal waves, each line represents a crest. So, in a longitudinal wave, just to draw this off to the side, it's true that we have areas of more densely packed particles, and then we have some areas of less densely packed particles, and then areas again of greater density particles, and then areas that have less particles. We call these areas with less particles rare fractions, and we call these areas with more particles compressions. Now, because of this, most people went with C, but I'm going to explain that that's not actually the correct answer here. What we're looking at here is when we draw a longitudinal wave in terms of the pressure and the distance, is that these areas of compression actually end up being our crests, and these areas of low pressure end up being our troughs. And then up here we get another crest, and down here we'd have another trough. And so this is how we learn to draw the diagram for a longitudinal wave and show that it can be drawn very similarly to a, where this lines up with that, there, and there, where this can be drawn very similarly to a transverse wave. Now, what that means in terms of wave front diagrams is that where we have a crest, we draw a line. So we would have here two crests, And we can see later on we would have a third. But what we notice is that they're still evenly spaced out. In diagram A, essentially each line represents a compression and each space in between represents the rarefaction. So it's still compression, rarefaction, compression, rarefaction. Happening in even intervals, and that's actually required for a wave, that it's cyclic, it's occurring at a constant rate. So A actually represents compressions and rarefactions happening consistently one after another. So the answer is A. C is a bit tricky because it has the shape of a longitudinal wave, but longitudinal waves don't look like this when they're drawn in a wavefront diagram. And then B and D, unfortunately, are not correct because of their shape. We draw wavefronts flat, not with a curve to them, even though waves physically look like they may have a curve. So, there's that. Okay, a radio wave of wavelength 60 centimeters has a frequency of about, okay, so if we're talking about a radio wave, we are talking about electromagnetic radiation, which we know has a speed. V is equal to 3.00 times 10 to the 8 meters per second, just like light, all electromagnetic waves. And you're given that the wavelength is 60 centimeters, so your wavelength is 0.60 meters. So really, if you've gotten here, all it is a matter of using V equals F lambda and rearranging to solve for F. So your frequency is going to be your velocity over your wavelength, which is 3.00 times 10 to the 8 over 0.60. And when you do this, you'll get the answer of C, 500 megahertz. So of course the units here were a bit of a trick for people. The numbers were a little tricky. Just keep in mind, it has to be in meters, not in centimeters, which is what the answer gave. And also that our velocity is not 343 for the speed of sound. Even though radio waves are what we hear on the radio wave itself, you don't hear them just buzzing through the air. It's actually an electromagnetic wave with a speed of 3.0 times 10 to the 8. All right. Rarefactions are best described as, and this is kind of just a definition, so we're just going to go through this one. A rarefaction is best described as, and the answer is C, the region of space between the with the largest separation of particles in a longitudinal wave. And then number 6, which of the following wave characteristics remains unchanged as a wave crosses a boundary into a different medium? So we've looked at this and we said which of the following cannot change when we change medium. Well, we've seen from our wave diagrams, if we draw from a low to a high density medium, if we send in a pulse on the way out, after the change in medium, we would see that here we had a wave with a shorter amplitude, a lesser velocity, and a shorter wavelength. And the returning wave would be out of phase. It would have the same approximate, I guess, yeah, this one would have to be a bit bigger here. Same approximate wavelength as before, out of phase. So what we've noticed, we've already definitely had a change in wavelength. This wave is much shorter, so it couldn't be wavelength. There's definitely a change in velocity, and there's a change in amplitude. So very quickly we realize the only option is frequency, and we've stated that before. You cannot change a frequency by changing medium. It would require waves to be produced somehow in between the medium. If 3 waves went in, 3 waves have to come out. You couldn't have 5 waves coming out. Waves would be created out of nothing. We know that's not true. So that's the answer for question 6. All right, question 7. If a 1 meter long string is vibrating in a standing wave pattern with 4 nodes observed between the fixed edges, which of the following locations, measured from either fixed edge, could the string be touched without disturbing the motion of the string? What the question is really asking for is saying, okay, we've got a string here, and between the fixed edge we have 1, 2, 3, 4 nodes. So my nodes are here, 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 and here. All right, so this string is known to be exactly 1.00 meter long. And as this wave oscillates, it's going to oscillate between the position I've drawn and this position I'm drawing out right now. And this is the pattern of a standing wave. So, as it's rotating back and forth, the nodes are the spots that produce no motion. If this was a slinky, these points here would have the most displacement in the slinky. Here, 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 here are all areas like that. But these circled nodes are areas where the slinky would relatively not be moving at all. And so that'd be the safest spot to touch without disturbing the wave. So how far from the edge do you have to reach? Well, you essentially have 1, 2, 3, 4, 5. You can break this string up into 5 equal spots to describe the distances. 1.00 meters divided by 5 gives me that each node is a separation of 0.2 meters. Alternately, you could also go and find the wavelength of this string, knowing that you have 4 nodes. You know that this is the 5th harmonic. So this is the 5th harmonic, and you know the length of the string is 1 meter. You can go and find the wavelength. This would give you a wavelength of 0.4 meters. You can try that if you'd like. But if the wavelength is 0.4 meters, the separation between nodes is still 0.2 meters. Get us to the same spot. So, starting from either edge, you'd have to move either 0.2 meters, or 0.4 meters, or 0.6 meters, or 0.8 meters to reach a node. And the only one of those options here is B, 0.2 meters. Okay, a student measuring the number of waves created by a leaky faucet dripping into a full sink counts 20 drops per minute. What is the period of the waves created in the water below? So the period, T, can be described as the time over cycles. So, in our case, how many minutes, or how many seconds? So 1 minute, that's 60 seconds. And how many cycles? 20. So doing this, 20 cycles or 60 seconds for 20 cycles would give us a period of 3.0 seconds. That gives us with A. The important thing here is to realize that our units are all in seconds. So we have to convert that 1 minute into seconds. Alright, this last one was pretty tricky as well. I quite liked it. So a hiker shouts towards a vertical cliff at a distance of 539 meters away. The echo is heard 3.06 seconds later. Determine the approximate temperature outside. This is a tricky one. So keep in mind that, again, if you are here, and this is a wall, and you shout towards the wall, the air has to go, the compressions in the air have to go all the way to the wall, hit the wall, and then bounce back. So the total distance traveled is not 539, but actually doubled that. And that gives us 1,078 meters. Now, we know how that the velocity is going to be described as the displacement over the time. So the velocity of this air happens to be 1,078 meters in 3.06 seconds. Now, quickly grabbing a calculator, we can figure out what that's going to be. Not the number shown currently. There we go, 1,078 divided by 3.06 gives us 352 point a bunch of stuff. But in our question, we only ever have 3 significant figures, so we're just going to leave it at 352. So 352 meters per second is the approximate speed. Now, from here, what we have to do is go under the assumption that, well, not under the assumption, we can use our equation for temperature, which was on the board as well. So the velocity of air is always going to be, of sound, sorry, is going to be 331 plus 0.6 times the temperature. In this case, we want to solve for the temperature, so we can rearrange. V minus 331 is equal to 0.6 times the temperature. Now dividing by 0.6, V minus 331 over 0.6 gives us our temperature. So plugging all that in, 352 minus 331 over 0.6 gives us approximately 35 degrees. And that leaves us with the answer D. Alright, so I hope you've enjoyed the multiple choice section of the quiz and the answers that are involved in that. Thank you very much.